method of superposition. When a beam is subjected to several loads at various positions along the beam, the problem of determining the slope and the deflection usually becomes quite involved and tedious. This is true regardless of the method used. However, many complex loading conditions are merely combinations of relatively simple loading conditions. So the first diagram, we have a concentrated load at a certain point with a span L, and it is a cantilever beam. And another beam, which is a simply supported beam, a combination of a uniform load and a triangular load with a concentrated load at point A or a distance A. If it is assumed that the beam behaves elastically for the combined loading as well as for the individual loads, the resulting final deflection of the loaded beam is simply the sum of the deflections caused by each of the individual loads. This is the cantilever beam with a concentrated load and a uniform load at the same time. We will separate the concentrated load plus the uniform load, and that's the method of superposition. In this diagram, we have a concentrated load, a uniform load, and a triangular load, and a combination of three loadings: a concentrated load, a uniform load, and a triangular load. And for the principle of superposition, deformations of beams subjected to combinations of loadings may be obtained as the linear combination of the deformations from the individual loadings. Procedure is facilitated by tables of solutions for common types of loadings and supports. In this example, we have a uniform load and a concentrated load, and it is equivalent to a concentrated load at 2 meters from point A plus a uniform load of 20 kilonewton meter. And the combination of two loadings in terms of deflection is the total deflection of the beam. Example: determine the midspan deflection of the beam if E is equal to 10 gigapascal and I is equal to 20 times 10 to the power 6 millimeter exponent 4. We have a simply supported beam with reaction 1 and reaction 2, and a uniform load of 1 kilonewton per meter from point 1 to point 2 with a distance of 4 meters, and a concentrated load of 2 kilonewton from point 1, which is a distance of 1 meter. By using method of superposition, we can determine the midspan deflection. The beam formula for, we have two combinations of loads, a uniform load and a concentrated load. And for the maximum beam deflection based on the concentrated load, we have the formula PB times 3L squared minus 4B squared all over 48 EI, where A is greater than B. So we have a combination deflection at midspan is equal to the total deflection of a concentrated load and a uniform load, which is deflection at concentrated load and designate as at 1 plus deflection at 2. So this will be deflection 1 and this is deflection 2. Then the formula for the deflection 1 with a concentrated load P, which is 2 kilonewton, that's PB 3L squared minus 4B squared all over 48 EI, while deflection 2, which is at a uniform load, the formula is 5W L exponent 4 all over 384 EI. And then we substitute. So P, that's 2 kilonewton, so 2, and B is always the shorter value And in this case, 1 meter is equivalent to B. So that's 1, open parenthesis, 3, and that length is equal to 4 squared minus 4 times B, which is 1 meter, and square, and divided by 48 EI, plus 5, and W, which is a uniform load of 1 kilonewton per meter, so that's 1, and L, the span, that's 4 meter exponent 4, and we divide by 384 EI, and then simplify. So that's deflection maximum, or at midspan. So that's 2 times 1 times 3 times 4 times 2, 3 times 4 times 4, or 4 times 4 squared is that 16 times 3 minus 4 times 1 squared all over 48 EI. And this is equivalent to 11 over 6 EI plus 5 times 1 times 4 to the fourth all over 384 EI, and that's equivalent to 10 all over 3 EI. 11 over 6 plus 10 over 3 meter to millimeter, that's exponent 4, so that's 1000 exponent 4, and then we divide by the value of E. The value of E is 10 gigapascal, or that's 10,000 megapascal, so that's 10,000, and multiplied by E, or I, that's 20 times 10 to the power 6 millimeter to the fourth, so that's 20 times 10 to the power 6. And deflection midspan is equal to, so that's 11 over 6 plus 10 over 3. The value is multiplied by 1000 exponent 4 all over 1000, or 10,000, and divide by also by 20 times 10 to the power 6. And the value for deflection at midspan is equal to 25.83 millimeter. And this is the answer. Example: the beam has a rectangular cross section of 4 inches wide by 8 inches depth. Compute the value of P that will limit the midspan deflection to 0.5 inch. Use E is equals to 1.5 times 10 to the power 6 psi. In the diagram, uniform load of 2,000 pounds per foot. So let's convert first. At A, and designate this as A, and this is point B. At A, the moment is equal to P times 2, so 2P plus a uniform load of the overhang with 2 feet length, so that's 2,000 times 2, and then the resultant up to the point A, the distance is 2 over 2, that's 1, and M is equal to 2P plus 4,000, and that's the moment at point A. It is also the moment at point B, so that's the end moment. Now that we determine the end moment at A and point B, that's 2P plus 4,000, or equal to M. So this is the diagram, so that's M, and it is counterclockwise direction, and the other one is clockwise direction. The cross section, that's 4-inch wide and 8-inch depth. So we'll find first the moment of inertia, and the moment of inertia for a rectangular beam, the formula is BD cubed all over 12. The width, which is 4 inch, and the depth, that's 8 inches and cube, we divide by 12, and moment of inertia is equal to, and the combination of the superposition, the value for the deflection of the uniform load, and the moment of, or the end moment for both sides. The maximum deflection for midspan is equal to 5W_L exponent 4 all over 384 EI, while that's at uniform load, and at moment, which is the end moment, the formula for midspan, or deflection for midspan, so that's ml squared all over 16 EI, both for the end moment at the left and moment or end moment at the right. And to find the deflection at midspan using the method of superposition, so the moment or deflection at midspan is equal to the summation of all deflections, and we have the deflection for uniform load, so that's 5W_L exponent 4 all over 384 EI, and the direction is downward, while the end moment at the left, the deflection is upward, and we will designate that the opposite sign should be negative, so that's ml squared all over 16 EI, and this is for the left end moment, while the end moment at the right direction is clockwise direction, and this will be multiplied by 2. So this will be the total deflection at midspan with the combination of a uniform load and an end moment. 5 times the uniform load, that's 2000. L, the distance L is 10 feet, and exponent 4. And we divide by 384. E is 1.5 times 10 to the power 6, so that's 1.5 times 10 to the power 6. And I, which is the moment of inertia, that's 512 over 3. 512 over 3 in inch exponent 4. We convert 10 feet to exponent 4. That's 1 foot or 12 inches. So that's 12. And we have 2000 pounds per foot. So that's, we will extract 12 exponent 3 minus twice of m, which is the end moment of 2p plus 4000, 2p plus 4000, and L is 10 feet squared, and we divide by 16, and E, that's 1.5 times 10 to the power 6, and I, 512 over 3, and we convert foot to inch, and this will be multiplied by 12 cube. The unit here is pounds foot, and this is 10 foot square, so that's 12 inch for 1 foot, and it's cube. And simplify, and the value for deflection at midspan should have a limit of 0.5 inch, so this will be equivalent to 0.5 inch, and this is 0.5. 5 times 2000 times 10 to the power 4 times 12 cube all over 384 times 1.5 times 10 to the power 6, and multiplied by 512 all over 3 in terms of fraction, so that's 225 all over 128 minus, So 2 times 10 square all times 12 cube all over 16 times 1.5 times 10 to the power 6 times 512 over 3. So that's 27 in terms of fraction, and multiplied by 2p plus 4,000, and we divide by 320,000. So 320,000 times zero point 0.5, so that's 160,000 is equal to 225 times 320,000, 128. So that's 562,500 minus 27 and multiplied by 2p plus 4,000 and close parenthesis. 27 times 2p plus 4,000 is equal to 562,500 less 160,000, so that's 402,500, and simplify, so that's 2p plus 4,000 is equal to 402,500 divided by 27, 10,907.4, and p is equal to 10,907.4 divided by 2, 5,453.7, and the unit is in pounds. So that's the value for p using the method of superposition.